Today, then we're moving on from our organic chemistry. We're not going to talk about all that other reactions and things that are in the book and those many chapters that I think are color-coded blue in the middle of the book. No, green, sorry. All the green chapters, we're not getting into all that stuff. We're only worried about functional groups. So we're going to skip on now to the first chapter of the blue section, which is carbohydrates, talking about sugars. And sugars have really, I don't want to say they're complicated structures, but their structures are such that it requires a little bit to be a little bit better at kind of flipping things around in our heads and seeing three-dimensional representations. So to help us with that, as we've done before, we're going to use our models. End up back here. So if everybody could take, let's do like 2 kits per table. All work together. Okay, so we're going to learn a new way of thinking about the three-dimensional structure of molecules. It kind of goes back to when we talked about isomers. And we kept saying, okay, are these actually constitutional isomers, meaning they're structurally different, or are they just look different because they kind of got flipped around on the board? Remember doing that kind of stuff? And we said, okay, we stretch them out, whatever. So we're going to do the same kind of thing, but we're going to use this term, rather than saying, are they the same or not, we're going to use this term superimposable. Anybody know what superimposable means? I think it's like a math term or something. I don't know. It means you can kind of put one on top of the other one, and everything has a corresponding match between the two. So you can look at 2 structures and show that they're the same by seeing that every bit of it has a corresponding same bit on the other structure. So like if you said, let's do an example. So these 2 markers, we would say they are superimposable because I can put one on the other one, and every little bit of one of them has a corresponding bit on the other one that's the same. But if I was looking at, I don't know, a different kind of marker here, these would not be superimposable because they aren't quite exactly the same. They're lined up. So that's what that word means. And that's what we're going to use when we construct these models. So take out 2 of the black carbon pieces and put 4 sticks in each one so that you have like the 4 bonds. If you have enough pieces, try to use the same size sticks, but if you don't have the same size sticks, it's not a big deal. Just put in whatever you've got. It doesn't matter if they're longer or shorter sticks, but it does make it a little clearer if they're all the same size. So, just like that. Make sure that it's the regular black balls with the 4 holes. Some of these kits have these like big balls that have side holes too. Don't use those. These things that have like 6 instead of 4, don't use those.
How many quizzes do you have?
Probably 2 or 3. Sorry, everybody got those? Okay. So are these two molecules superimposable?
Yes.
Yes. You put them like right like this. You can see that each one has a corresponding other part that are the same, right? Okay. All right. Take one of the small balls, which we called hydrogen. These little round ones. Careful, they bounce away pretty easily. You hear them going. And put one on each molecule. Just one. Are those still superimposable?
Yes.
They are. Okay. All right. Now, take one of a different kind of ball. So that could be a light blue one, or a red one, or green, or whatever you've got. Something different, and put one on each molecule again.
The same one.
The same color on each, yeah. If you don't have two of any one thing, there's some extra pieces up here you can grab. Are those superimposable?
Yeah.
Still superimposable, yeah? Okay. So now here's what we're going to do. Take your two models and point them so that they are kind of like mirror images of each other. So you can imagine one of them is looking in the mirror and seeing the other one. And the two sticks that have nothing on them are kind of pointed at each other like that. Everybody see that? All right. So when you've got that, take a different color, whether it's red or blue or gray or whatever you've got, a different color, and put one on each molecule to maintain that mirror image relationship. So if I put this one here on the one that's coming out, I want to also put this one on the one that's coming out. So they continue to look like mirror images like that. Everybody do that? Okay. Are these superimposable?
Yeah.
Do it. Superimpose them. Put one kind of on top of the other one and make sure everything lines up properly. Doesn't work, right?
Well, see, that's what you were saying. Because, like, if it's a mirror, then what do they be on the opposite side?
Well, that's exactly the thing. Is some things have a mirror image that is superimposable, and other things have mirror images that are not superimposable. So before we put that red one on there, you had mirror images, right? Still mirror images, but they're superimposable mirror images. Once we introduce that other one, we've now broken that symmetry and formed non-superimposable mirror images. Because now we can't, when we try to put them together, we can only get two of the things to line up, and then the other two are always opposite. So we can line up like the red and the stick, and then the other two are not, don't work out, right? So that actually turns out to be a really important point when we're talking about brittle molecules. Those are different molecules. And the definition of isomer that we have so far doesn't really help us here, because these are actually, like, assuming these were whatever they were, they would have the same molecular formula, one of each of these types of things. They would also have the same connectivity. The atoms are connected to each other in the same pattern, but they're still not the same. So we need another way of expressing that these things that are connected the same, have the same formula, but are still not the same. And the word for that is stereoisomers. Stereoisomers have the same formula and the same connectivity, meaning the atoms are all connected the same way. But a different three-dimensional structure. So if we look at these things in 3 dimensions, we can say, okay, yes, they are not the same. Even though they have the same formula, they're connected the same way, they are still not the same because of the arrangement of atoms in 3 dimensions. So another word that we sometimes use for that is arrangement. We have the same atoms connected in the same way, but arranged in a different way. All right, let's try to draw these things then. So now it's not good enough to go so I'm going to make a circle for my ball one, and I'll call them blue and red. You can call them whatever you did, or you can follow my example, whatever. But that's not a good enough structure. That type of structure doesn't give us enough information because it doesn't tell us how the thing is arranged. We could be looking at it from the front, from the back. So this is when we need to start using that three-dimensional structure that we learned a couple weeks ago. All right, so I'm going to put these so that I can see the three-dimensionality of it, and I can see the mirror. So I can see the mirror images, the way that we set them up initially. However you set yours up, you can do it your way. But I'll leave those there, and we're going to draw those next to each other. So when we draw them, we need to think about that the bond coming up and the one kind of going straight out are in the plane, we would say. So they're flat together. And then this red one is pointing out that way, and the blue one is pointing back this way. So for those of you who can't see, that's the way I have them set up. And those ones facing inside are pointing, the red ones are pointing towards you, and the blue ones are pointing back. So let's use that dash wedge notation to express that here. So we'll have our C in the middle, our open stick with nothing on it going up, the one with the ball on it going back and to the left. And then we'll have the blue one going back away from you, and the red one coming out toward you. And this is why it's important to use that dash and wedge notation. If we didn't use that, if we just use straight lines, it wouldn't be clear which direction is which one's coming out, which one's going back, and that could potentially switch our two stereoisomers. So we could be drawing the opposite one of what we actually want to draw. Let's draw its mirror image right next to it. Yeah.
So in like notes before, you did carbon double bond with hydrogen and then H3.
Mm-hmm. Same idea, yeah. With double bonds, it's a flat, it's not a three-dimensional thing, but the same idea. They're connected in the same way. They still have the same connectivity, but a different structure, a different arrangement, because we had them either like going up here or going like this, because double bonds can't rotate. But we were doing that in 3 dimensions instead of 2, is the difference. All right, so let's redraw these then. So those are our mirror images, and we're saying those are different. Those are not the same. Now, when they're drawn like that, it's hard to tell that they aren't the same. In fact, when we built them and I asked if they were superimposable, almost everybody said yes. Because when you look at it like that, they look the same. So to see the non-superimposable nature of them, to see that they're actually different, it helps to flip them around the way that we did physically with them. So if I take one of these and I flip it around like this, now we can see more clearly that they are different. For those of you who can see. So instead of looking at them as mirror images like this, I flipped them around like this. And now you can see that the red and the blue do not line up with each other. So let's do that on paper too. We're going to spin this one around 180 degrees. And that means the O is going to end up over here, just like with the first one. And the dash and wedge ones are going to be over on the right. But think about where they're going to end up. If the blue one in the back goes 180 degrees, it's going to end up in the front. If the red one in the front goes around 180 degrees, it's going to end up in the back. If you can't visualize that, check your models. Grab your models, line it up that way, and then think about what happens when you turn it 180 degrees. You should see the red one ending up in the back and the blue one ending up forward. So the opposite of what they were on the other side.
Are we going to be able to use these models?
Yeah. There's no.
Now, come on, you'll get it.
Wait, we can?
What?
We can't use these models on the test?
Don't you have to do it in your head? So
No,
it's
I
easier.
can't do that.
Sure you can. You'll get there. Maybe we can use the models on the test. Yeah. I don't necessarily have a problem with that, but I think you can do it. It just takes a little practice, flipping things back and forth. All right. So now, if we look at this one and this one, we can see that they're actually switched. That while two of the things connected are in the same place, the other two are definitely switched. And we have a special name for those. They're called enantiomers. Enantiomers are non-superimposable mirror images. So if you can make a mirror image of something, and that mirror image is not the same, not exactly superimposable to the original thing, then you have a non-superimposable mirror image, and therefore those two things are enantiomers. So a good example of that is your hands. Your hands are mirror images of each other. Do it this way so you don't have to look at micro stitches. Your hands are mirror images of each other, but they are not superimposable, because if you try to line them up, they don't quite line up. One's always going to end up being opposite. Some part's going to be opposite of the other part. So that makes those non-superimposable mirror images. And when that happens with molecules, we call them enantiomers. So enantiomers are a type of stereoisomer where they are exact mirror images.
Wait, so these are enantiomers?
Mm-hmm.
So for like an exam question, like how would you question something about on this topic? Are you gonna put
Yeah, well, what do you think? How would you do it?
Got your models.
the models and ask what they are, but I don't know if you'd actually make us raw.
Yeah, so one thing I might do is, you know how we, in the last exam, we talked about, or there were a bunch of questions that said, are these two things isomers, or are they the same, or are they just unrelated? So in this, it could be, okay, here's a couple structures. Are they stereoisomers, or are they enantiomers? And you could figure that out by rotating them, flipping them around, redrawing them such that you can line up most of it and see if it can all be exactly superimposable, or if there's still going to be some stuff that's not superimposable. So that's one way, just sort of manipulating the objects to see if they're superimposable or not.
Is there some kind of quick way of figuring that out?
Um,
If there's like a certain amount of atoms there? Or?
Yeah, kind of, and we'll see that when we get into larger structures. The quick way of figuring it out is doing on paper what we just did with the models. So spinning them around, turning them around, redrawing them, so that you can line up as much as possible. And then if there's anything else that's still not lined up, then you know that it's not the same. So if you're looking at these two structures, and you want to know, are they enantiomers? Well, we know they're mirror images, but then the next test is, are they superimposable or not? So you need to turn one of them around so that you can compare them directly and see, oh yeah, they're definitely not the same. So that's how you put those together. And we'll see with larger molecules how we can do that. So actually, let's just do that now before we get into the carbohydrates. So let's look at a molecule like this. This molecule is called tartaric acid. So it's got 4 carbons. The 2 left and right sides are carboxylic acids. And then in the middle, it has 2 of these carbons that have the OHs coming off of them, where the stereochemistry is specified, meaning we're saying specifically this one that I drew has the OH coming out and the H going back. And that's true on both carbons, OH coming out and the H going back. Everybody see that one? Okay. So the question is then, is this the same as its mirror image? Is it actually identical to its mirror image? So let's draw its mirror image. We're going to pretend there's a mirror right there, and it's looking into the mirror. We're going to draw everything just exactly opposite as what we see here. All right. Do you see how that's exactly opposite? How those two are as though one is looking in the mirror at the other one? So everything has a related one on the other side. So they look pretty similar. But the question is then, are they actually the same or not? Are they superimposable? So the way I have it drawn right now, it's kind of hard to tell. Because if I grab this and I move it over to here, okay, I didn't draw it exactly the same, but you can tell that it's not superimposable. It's like the way I have it drawn, it's kind of the opposite. Do you see that, how they don't quite line up? Maybe it's clearer even if we don't do that. We just say, okay, so this OH kind of goes up over here, whereas this one goes down. This one's coming off the up like that. This one's going down. So it's definitely not comparable the way I have drawn it right here. So we have to think about, okay, how do we get this in a form where we can actually see if it's the same or not? And one way we could do that is by flipping it over. So let's try it with models. So get together with the group across the table from you, or maybe you two can do this so that you have enough pieces for this. And we're not going to build the entire thing. We just want to build enough so that we can tell, we can compare them. So each group build a chain of 4 carbons. To start with, remember there should be a little rubber sleeve in your thing if you have trouble taking them apart. All right, so build a chain of 4 carbons and have each of the 2 groups build a chain of 4 carbons, so that, because what we're going to do then is one group's going to build one and one group's going to build the other. So build a chain of 4 carbons. Everybody build a chain of 4 carbons. And let me highlight those 4 carbons here. So we're talking about these 4 carbons. Everything else connected is not carbon. So those are the 4 we're building. Now decide amongst yourselves which side of the table is building the left molecule and which side of the table is building the right molecule. And here's how we're going to do it so that we don't spend too much time, we don't get confused. Yeah.
So the garden ones go left.
Right. All right, you got your 4? You got your 4? Everybody got your 4? Okay. So whichever one your group is doing, make sure that your chain of 4 is in the exact same orientation as what you see up there. So if you're on the left, it should start at the bottom and go up, down, up. If you're on the right, it should start at the top and go down, up, down. See that? See how the two chains are upside down from each other? All right. So take whichever one you're building. And then here's what we're going to do. Since those middle ones are the only ones that actually matter in that they have the dash and wedge thing, they're the ones that control this weird three-dimensional geometry, we're only going to put an OH, which we'll just say is a colored, so take some other colored one, and we're going to add OHs to the middle carbons. So here's how I'm going to do it. Let's say I'm doing the one on the left. I line up my structure like this. Okay. I get my OH ready. I'm going to put it on the second one, and because it's on a wedge, I'm going to make sure that it's on the one that's coming out at me. See that? So the wedge means coming out, and everybody's going to be doing wedges because both sides of the thing show them coming out at you. So I'm going to do the same thing with the next one. What? The OH. So we're going to say this is the OH. We're just going to ignore the rest for now. And so the same thing on the bottom one then. I see the OH is on the wedge, so I'm going to show that coming out at me. So if I'm on the left, this is what my thing should look like.
So we're not doing.
These are the oxygens. We're not going to do the end ones. The end ones don't affect it because they don't have the dashes and the wedges. We're just going to do these two, so you can see that. So if you're on the left, this is what yours should look like. If you're on the right, it should be similar but kind of like flipped. You see that? Look at it one more time and make sure that it's set up the way that it should be. Now this one's coming out. You want it to go toward you. There you go. Any other questions? Anybody else having trouble getting these together? Does that work? Okay. So now compare with the other group and see if you actually made the same thing or not. See if they're superimposable. Don't disconnect anything, but line them up and see if they line up properly. No, because they go to the right there. On the left, this one should be up. So it should go up, down, and just be
Oh, good.
You've got them on the wrong.
So it's a.
You're doing left.
Yes.
You've got the zigzag coming up, down, up.
You made cheese.
And then the middle two.
It's just the circle.
It was possible.
So did anybody figure it out? Are they superimposable or not?
No.
They're not. Correct. So that means that those molecules are not the same. And they're actually enantiomers. Yes.
What's the difference between these two?
For us, nothing yet, but this is a more specific definition of this. There are other types of stereoisomers that are not exactly just we haven't looked at it.
But as of right now.
As of right now, they mean the same thing.
Okay.
All right, so we got those worked out. So now let's talk about how we do it on paper. Now with larger molecules like this, it's actually a little easier, I think, than what we did with the small molecules when we were twisting them around. So here's what we're going to do. We want to flip one of these molecules over. We want to either flip it this way or we want to flip it this way. So that's what you did when you tried to line them up. So which way do you want to go? Which way seems more reasonable to you? Flip it over like this or flip it over like that? Flip it down? Okay, so let's flip it down. So imagine taking everything on this molecule from up here and flipping it down that way 180 degrees. And let's take it step by step so we can actually see what's happening here. Everything that's going down at some angle is going to end up going up at the exact same angle. So let's start on the left side. We had this OH here that's kind of angled down from here. So now it's going to be angled up when we flip it over. This was straight up, so now it's going to be straight down when we flipped it. And then we can follow the rest of the zigzag the same way. If you want to keep going step by step with each atom, that's okay, but once you got the zigzag kind of going the right way, you can just follow it along back and forth. All right, so now we have to add those dash and wedges. So take your model, whichever one you did, and let's look at what happens to the wedges when you flip it over. So what happens to wedges when you flip them over? Wedges become, yeah, they go to the back. So if they were coming out front, they're going to end up going back. So everything that was coming out front is now going to be coming out back once we flipped it. So let's do that. So here we had an OH coming out front. So instead it's going to be an OH coming out back. We had an H in the back, so we're going to end up with an H in the front. On this one, we have an H. We had an H in the back, so now it's in the front. And we had an OH in the front, so now it's in the back. So you'll notice that there is a nice rule here that whenever you flip a molecule over, all the dashes and wedges switch. Flip the whole molecule over, everything on a wedge becomes a dash, and everything on a dash becomes a wedge. So no matter how big the molecule is and how many different things it has, if you flip the molecule over, all the dashes and wedges just switch. It's always going to be like that. Which way you flip it is going to change nothing. Yeah, it's going to if you have an asymmetric molecule, it's going to matter. So if you have like on this molecule, it's got the same thing on both sides, that carboxylic acid on both sides. If the carboxylic acid was only on one side, if you flip it over like this, it stays on that side. If you flip it over like this, it goes to the other side. So, yeah. All right, so now if we compare the flipped molecule here with this one over here, you can see pretty clearly that they're different because the dashes and wedges are opposite. You see that? On the left, the OHs are on the wedges. On the right, the OHs are on the dashes. And so those are not the same. Those are enantiomers. All right, how's your brain?
Hurts.
Hurts? In there? Okay. So now let's apply this to carbohydrates. The reason we just messed with all that is because carbohydrates, different sugars, only differ by these well, not all of them, but big classes of them only differ by these types of relationships. So they mostly have the same structure, but only the dashes and wedges change to give you totally different sugars that interact with your body and with other systems in totally different ways. So we don't have a lot of time left. Let's just take a look at a simple one. So we know carbohydrates because they're processed by your body to give you energy. They're stored as glycogen and eventually go through some processes, some metabolic processes, which I don't think we're going to get to this semester, to become ATP and to deal with stuff like that. Does anybody know where this word carbohydrate comes from? Can you guess? Carbon and
Hydrogen.
close. What does hydrate mean?
Water.
Water. So it's carbon and water. So most carbohydrates have a formula that is something like carbon and then a certain amount of water. So for example, glucose, which is C6H12O6. There's a bunch of other sugars that are also C6H12O6, as we'll see, since they're all stereoisomers. We can split that up into C6H2O6. We know we wouldn't normally write it that way, but if we regroup the H's and O's and stuff, it has the same numbers. So back in the old days when these things were first getting discovered, what they would find is that they could kind of get a certain amount of water out of it, and that's why they named it carbohydrates, and what was left was carbon. So when you took the water out, what you had left was carbon. So therefore a carbohydrate. Oops, let me, all right, so the simplest carbohydrate is a molecule called glyceraldehyde. And it looks like this. So as we're going to see on Thursday, since we're almost out of time, carbohydrates generally have the same structure, at least these simple sugars or monosaccharides. They're going to have an aldehyde on the top. And then the other carbons in the structure all have an H and an OH. And then the very bottom of the chain is going to have two H's and an OH. So each carbon has an OH on it, except for the top one, which is an aldehyde. And then the bottom one has the extra hydrogen also. So this is a very kind of general representation of glyceraldehyde. If we take a look at that as a line structure, we'll see that there's actually two types of glyceraldehyde. So there's our aldehyde. Actually, you know what? Let me rewrite that. Let's keep this vertical orientation. We'll see why in a little bit. So here's our aldehyde on top. And then there's an OH on the bottom. And then this OH in the middle actually matters in terms of the stereochemistry. So there are two types of glyceraldehyde. One with the OH in the front and one with the OH in the back. I'm running out of room here, but this one would be called L glyceraldehyde, and this one would be called D glyceraldehyde. They are enantiomers or stereoisomers, and we'll get into in a minute why they're, or how you know which one's D and which one's L. Pretty much all naturally occurring sugars in the world are all the D type and not the L type. So the L type can interact with living things and living systems in a totally different way than the D type would. So for instance, it may not taste the same to you, to your taste receptors. It may not have the same functions in your body. It may not go through the same type of metabolism that the other ones go to, only because of that little change of the three-dimensional orientation of which OH is on the wedge and which OH is on the dash. So because this is so important to sugars, a system was devised so that we don't always have to be thinking about, like, okay, flipping this thing over to see if it's the same as this other one. And the system that's devised is called Fischer Projections. And I think I don't want to get into it yet because we only have 2 minutes to go. So we'll just save that for Thursday. This stuff will not be on the quiz on Thursday. We'll keep working on this. This will be next week's quiz. So focus on functional groups for now to get ready for the Thursday's quiz. And then we'll have more time to practice with this before next week. All right, so we'll stop there, and we'll start lab at 2. For lab today, we still have to measure the stuff from last week. So that should still be in your drawers, should still be okay. And then we'll do the lab today, which should be okay.
You always pick it up? Usually. But there's not.